Hello everyone. Today our group would be covering the paper on single photon advantage in quantum cryptography beyond quantum key distribution. Basically, whenever we talk about quantum cryptography, the major conversation revolves around QKD, but it has a very specific and limiting assumption that Alice and Bob both implicitly trust each other and they are teaming up together to stop an outsider Eve to prevent any sort of information leakage. But in real world, many cryptographic tasks involve parties that do not trust each other. For example, let's say digital contract signing or online casinos, or let's say an election of a randomized leader. In all these scenarios, there is no outside hacker, but the real threat is the person sitting across the network with us. So here, Alice doesn't trust Bob, and Bob doesn't trust Alice. So basically, QKD has a fundamental issue that trusted parties should cooperate, but which is useless here. So we have to look beyond QKD, and hence this paper is all about that. So whenever we talk about distrustful parties, the concept of coin flipping comes in. The concept of coin flipping is such that it is regarding two spatially separated parties which do not trust each other but need to agree upon some random binary bit for some communication. Suppose if Alice just flips a physical coin and tells Bob that it is head, then there is no way for Bob to believe or to reason on that fact. So classical cryptography solved that by using a one-way function, a complex math function, but it assumed that the Bob, for example, the adversary has limited computing power. What if Bob could have access to quantum computer? He can break the match, he can manipulate the protocol and force the coin to land on tails. To achieve this and to have the unbreakable fairness, we have to rely on the rules of physics rather. So this paper is all about quantum strong coin flipping. Basically, in weak coin flipping, parties have opposite choices. So let's say Alice wants zero, Bob wants one. But in quantum strong coin flipping, neither parties have their known preferences. They just want a perfect random 50 is to 50 outcome. This is incredibly hard to implement because the protocol has to act like a two-way mirror. Like it has to guard against cheating in both the direction simultaneously. So to execute quantum coin flipping, Alice sends a quantum state encoded as photon to Bob, and previously scientists have done that using photons from, let's say, heavily dimmed weak coherent sources, weak coherent pulses. So if you look at the screen, the plot shows that laser light follows a Poisson distribution represented by blue bars. But if you dim laser down so that the average pulse releases one photon, the physics says that occasionally the laser could emit one or two, let's say two or three photons at that very exact moment, and you can see this in the highlighted red zone on the graph. If you are dealing with a distrustful adversary, these multi-photon events are not reliable. Suppose if Alice accidentally sends a pulse with two identical photons, Bob can intercept it, use a beam splitter to separate them, and measure one photon to figure out what Alice's secret state was, and keep the other photon perfectly and let it execute the protocol. Then Bob gets a cheat code because of the laser's imperfection. Quantitatively, for weak coherent pulses, the photon risk is not exactly zero. You can see probability for multi photon uh, lasers that even for small mu, the term is non-zero. Basically, mu is the mean photon per pulse. So cheating opportunities still exist. Now in QKD, we also used dim lasers. Then why that problem was not arising there? Because QKD presents multi-photon problem using decoy states, where we intentionally vary the brightness of the pulses to catch Eve. But you cannot use decoy states in coin flipping, as in coin flipping, Bob is the attacker. If Alice sends a multi-photon pulse, Bob isn't going to report that anomaly to Alice back because he's just going to use that extra photon to cheat and get the task done in his favor. So we cannot use decoy state, we cannot use the lasers if we want a true security. Now, this leads to the title of paper, the single photon advantage. Instead of messy laser, the scientists used SOTA, deterministic single photon source. Specifically, they used a semiconductor quantum dot embedded in a microgravity that, and this device emits exactly one photon at a time. Again, if you see the green bars in the graph, you would notice that the probability of emitting two or three photons drop drastically to zero practically. So in quantum optics, we measure this using anti-bunching value G2 of zero. A standard for standard laser, it is one. For an ideal source, it's zero. And for the quantum dot used here, it was 0.03, proving that multi-photon cheating opportunities were virtually eliminated. Now, if you look at the single photon source, we can write that for probability of single photon source is near about G2 of 0 mu square by 2, and it is relative to weak coherent uh, by G2 of 0 factor. So if in this our case G2 of 0 was 0.03, the multi-photon risk scales down by a factor of 33 times. So this is exactly the security advantage this paper has leveraged. By eliminating these extra photons, the paper demonstrates single photon is very advantageous. It achieves a lower cheating probability and a higher rate of secure coins flip than both classical and the laser based quantum protocols. Now, basically, if you look at the qubit in quantum networks, we usually get the noise like some flipping occurred, polarization flip occurred, or photons are lost. This is known as quantum bit error ratio, or QBER, or simply qubit. In standard QKD, we can tolerate up to 11% of qubit, and Alice and Bob just talk over a public channel, use post processing or error correction algorithms to fix it. But in coin flipping, Alice and Bob don't trust each other. They are distrustful parties. Then they cannot do friendly post processing. In this, the if error arises, the protocol has to be aborted. So if the protocol has to be aborted too frequently because of such hardware noises, a cheating Bob can use that for his advantage. If Bob tries to cheat and it fails, he would just say that it was some noise due to hardware, and he would do that again and again until he gets its outcome. So this is wrong. So, because of strong quantum coin flipping, it is very fragile to handle if your hardware is not good. So, to achieve a quantum advantage over classical math, the qubit must be capped below 4%, and this paper achieves QBR of 2.8%, which is a huge improvement from previous attempts of 10% or more. And basically, I would like to clarify one thing, that for the whole notebook, in our case, we have used epsilon, the bias of coin flipping protocol, and the cheating probabilities of Alice and Bob as depicted by this formula. And basically, lower bias means fairer coin flipping.
Uh, Till now, we have seen the motivation behind quantum cryptography and why classical approaches usually fail in the distressful scenarios. So I'll take you through the protocol that works and how we actually define security in the setting. So first, what are the problem? What is the problem we are trying to solve? So assume there are two parties, Alice and Bob, who they don't trust each other, but they want to generate a fair random bit, like flipping a coin. And the challenge is neither Alice or Bob should be able to control the outcome, even if one of them tries to cheat. And this is what we call as the quantum strong coin flipping, where both the parties want a completely fair result. And the goal of this protocol is not to eliminate cheating entirely, which is not possible in the ideal scenarios, but to limit how much advantage a cheating player can get. Uh, Before going into the protocol, let me uh, explain few security definitions. The first one being honest winning probability, where this is the probability. that Alice or Bob wins when both of them follow the protocol honestly. Ideally, we want both of these to be equal or half, so that the outcome behaves exactly like a fair coin toss. And next, we have the cheating probabilities. Uh, it tells us if one of the player cheats while the other is honest. What is the maximum possibility that a cheating player can force their desired outcome? In classical system, this can go all the way up till one, meaning like a dishonest person can completely uh, control the result, of course. But in quantum systems, uh, this is fundamentally limited by the laws of physics. And and then we have something called as the honest abort probability. This is the probability that the protocol fails even when both the players are honest. This can happen because of the real world issues like photon loss, noise, or measurement errors. Instead of producing a wrong result, the protocol simply aborts and can be restarted. So, together we use these three quantities: the honest probability, cheating probabilities, and the abort probabilities, to define how secure and practical the protocol is. Uh, Now let us look at the fairness and first let me define what actually fairness is. Um, a protocol is called balanced if both the players have equal winning probability when they are honest, and it is fair if both the players have equal cheating power. uh, to quantify security, we use something called as bias. And bias is defined as a maximum cheating probability minus half. So it basically tells us how far a system is from a perfectly fair coin. So if the bias is zero, then no one can cheat at all. Uh, but interestingly, quantum mechanics itself puts a limit here. There's something called as the Kitave, Kita, Kitev bond, which says that the bias can never go below around 0.21. So here, even if the best possible quantum protocol, some level of cheating is unavoidable, but it is still much smaller than the classical systems. Now, let me take you to the protocol overview. Uh, So the main idea is to carefully structure the interaction between Alice and Bob, so that neither of them have complete information at any point. Both are forced to commit the choices, and any inconsistency can be detected in. So if you look at this diagram, it shows the flow of information between Alice and Bob. Uh, both quantum communication, both quantum and classical communication can be seen here. So I'll explain the step-by-step approach of this protocol. First, Alice prepares a quantum state where she randomly chooses a bias and a bit and encodes this information into a quantum state, which she sends to Bob. At this point, Bob doesn't know what the bias she used or what bit she encoded. Next, uh, Bob measures the incoming state in a randomly chosen basis. Now, this is very important because the bases are non-commuting. So if Bob chooses a wrong basis, the result is inherently uncertain. So this prevents Alice from predicting how Bob will measure. So, and then finally, Bob sends a random classical bit. This step is very crucial because it forces Alice to commit to her earlier choice before she knows Bob's bit. After that, Alice reveals her basis Alice reveals her basis and sh and the bit she originally encoded. Now Bob has enough information to check whether she is honest or not. So if Bob uses the same basis as Alice, he compares his measurement result with her claim. If there is a mismatch, the protocol aborts. So any cheating attempt introduces a risk of being detected. So finally, uh, so if everything is consistent, the outcome is defined as the XOR of Alice bit and Bob's bit. So this ensures that basically both the parties contribute equally to the final result and neither one can control the final result. So, um, so the reason this protocol works comes from the basic quantum properties. Quantum states cannot be copied. The measurement disturbs the system, and non-commuting bases introduce uncertainty. So, because of this, if a player tries to gain extra information or manipulate the system, they inevitably introduce errors, and those errors show up in the verification step. So, instead of preventing cheating entirely, the protocol ensures the cheating becomes risky and limited. So, now that we have seen the protocol is designed, how security is defined, uh, the next question is how well does this actually perform in practice, and what are the actual cheating probabilities, and how do different parameters affect them? And that is exactly what we'll look at the simulation part of this presentation. Yeah. Over to others.
So now I'm going to demonstrate the advantage of single photon source over the weak coherent pulses in a QSCF protocol. So weak coherent pulses, it is emitted from laser source, and the photons, like number of photons, follow the po- Poisson distribution in one single pulse. So this means that even if the average photon number, mean photon number mu is very small, there is still a non-zero possibility probability that there are at least like two or more photons emitted. This leads to the multi-photon event, and this is the major weakness for laser-based implementations of protocols. So why this is so? Because the reason is that the multiple photons, if they are emitted, then if a opponent is a dishonest party and they have the chance to do multiple readings and measurements, do more sophisticated measurements of the same quantum state, and the information they can get is more than like what was desired initially. So this increases the cheating probability of the like of the opponent, the adversary. So this is now in the contrast, we have single photon source. It basically emits only one photon at a time, and this the quality of such uh, for like source is determined by the parameter second order correlation function G20. G20 is basically measures the multi photon event. It suppresses the multi photon event, and it is zero for ideal single photon sources. So now, like now in single photon sources, the multi emission scales are directly proportional to G20. This like this says that the multi photon emissions are significantly fewer than what we had seen in weak coherent like like WCP, and like this we can see from the p multiple is equal to G20 by 2 mu square. And now how does this connect to cheating probability? So in quantum coin flipping, cheating is when the dishonest party gains more information than desired, and they are able to like affect the quantum state that was initially seen. And there are two main reasons for this imperfection. Those are multi-photon emissions and then QBER. QBER is basically noise in the system, like its full form is quantum bit error rate. And then we have like another parameter, protocol rounds. So protocol rounds, like initially if we send very small number of transmissions, there is a possibility that the they might get lost or they might not be detected by the part like opponent party. So there will be a possibility that about probability will increase. So to overcome that, we have uh, we have protocol rounds. So we use multiple rounds to generate a single coin flip, and these rounds are denoted by k. But the trade-off here is, even though now we have a reliable like, reliable source of sending the information, there is a increased chance of cheating, because every single round the cheating probability is accumulated, as we can see in the expression here, and this leads to the increase in total cheating probability. And now, thus the security of protocol depends, like, it not only on the photon statistics as we have seen above, but also in the photon, like, protocol rounds. So these are the probability models, uh, from, like, for a weak coherent pulse. As we can see, it follows Poisson statistics, and this is significantly higher than what we can see in SPS here. So the classical limit is taken from the paper. So now we are going to, like, plot the curves for this, and we also add an extra term here, like, for Cuber, and the parameters used are as follows: mu is equal to 0.0013, Cuber is 2.8%, and G20 is 0.03, and number of protocols, it varies over magnitude. So this is the graph we have got. Yeah. So in this graph, we can see that, like, we can clearly see that the black line, which is classical limit, and we have WCP and SPS here. The quantum advantage, which is like the cheating probability being lower than classical, we can see that for WCP it spans, like, for a very small number of k, but for SPS we can see that it spans for larger magnitudes of k, and this shows that it performs better for it performs better than WCP. And the dotted line is basically ideal SPS if we have like G20 is equal to zero, like zero, like, which means that only single photon is emitted at a time. But ideally, like, in real life, that is not the case. So that's why we have this curve. Yeah. And also we can see that the rate of increase in rate of increase in WCP is more than rate of increase in SPS. And then we also calculated the difference between for the difference between probabilities, cheating probabilities, like classical probability and quantum probability, over the mean photon number and protocol rounds. So as you can see, as the mean photon number increases for WCP, the quantum advantage, which is basically like cheating probability of classical minus the cheating probability in WCP, is decreasing as mu increases and mu and number of rounds increase. But this is not the case in SPS. The the quantum advantage is more, like, prominent in SPS, as you can see here. So yes, so what we can say from this is SPS, like single photon source, is better better than WCP when it comes to, like, giving the least imperfections in transmitting, and this actually helps in quantum security, because, like, the dishonest party can't figure out more information about the quantum state than that we have intended to send. Yes, this shows that the quantum coin flipping protocols, they don't not only depend on the protocol itself, the theoretical robustness, but they also depend on photon source. Say, like, for example, like the weak coherent pulses suffered from, like, intrinsic, like, multi-photon events due to their Poisson statistics, but the single photon sources, like, reduce this vulnerability, the cheating, so thus decreasing the cheating probability. Yes, thank you.
Hello everyone. I'm going to be covering the experimental setup part of this experiment. Basically, to give you a brief overview, we implemented a quantum strong coin flipping protocol. Basically, Alice and Bob want to agree on a random bit without either party being able to cheat. So the goal is here to bound their cheating probabilities below the classical limit, ensuring fairness. We encode the coin in the polarization of single photons. Rather than a single shot, each coin flip uses a block of k pulses, starting at 50k pulses for the zero loss back-to-back run and increasing at higher losses to maintain sufficient detection rates. Our setup has two main sites. Alice here uses a deterministic quantum dot single photon source and a fast electro-optic polarization encoder to prepare the photons in one of four protocol states. Bob, at the other hand, receives them using a passive basis polarization analyzer, which randomly routes the photons to one of four high-efficiency superconducting nanowire detectors. His time tagging electronics are synchronous to Alice clock. Here I mentioned the experimental baseline parameters. The system is clocked at 80 MHz. Importantly, the key protocol parameter is A equal to 0.9. This basically defines how our four polarization states are tilted relative to standard VB84 states, which is carefully chosen so that Alice and Bob have equal cheating probabilities in the ideal model. Secondly, covering the quantum dot source and the flying qubit generation, Alice uses a semiconductor quantum dot which acts as an artificial atom to emit exactly one photon at a time at 921 nanometers. This dot is deterministically integrated into circular Bragg grating microcavity. We operate this device in a cryogenic atmosphere at around 4 Kelvin using quasi-resonant p-shell excitation at 896 nanometers to produce a dominant charge exciton line. To verify its single photon character, we filter this emission into Hanbury-Brown and Twist interferometer. We measured the second order correlation at zero delay and we found it to be 0.03, which is much lesser than 1. Because this value is so close to 0, it proves the light is strongly anti-bunched and sub-Poissonan. Multi-photon pulses are extremely rare, which is exactly the secure single photon behavior we need to prevent cheating in the protocol. Moving on to explaining the source code, which I have written here. In our first code cell, we basically visualize the three key sources characterization from figure 3. The left panel here models the narrow charged exciton emission spectrum. The middle panel simulates the Hanbury-Brown and Twist histogram. We can see here the central peak at zero delay is heavily suppressed at 0.03, reflecting the extreme rarity of multi-photon events. The right panel, on the other hand, simulates the Mach-Zehnder coherence test. The flat line confirms that our quasi-resonant p-shell excitation produces zero photon number coherence, meaning Bob cannot exploit hidden phase relations to cheat. In my second and third set, we are basically comparing the quantum dot source to a weak coherent pulse WCP laser at the same brightness. In the second cell, we compare the security risk of our quantum dot source, the green line, and against a standard weak coherent pulse laser. By plotting the multi-photon probability against the mean photon number, we see that for any given brightness, our source produces orders of magnitude fewer multi-photon pulses than the laser. My final code cell demonstrates this clearly at our exact operating point of mu equal to 0.0013. The bar chart here basically shows that both sources provide the exact same ratio of useful single photons. However, the multi-photon probability, which is exactly what the cheating Bob exploits in a photon spilling attack, is drastically lower for the quantum dot. This explicitly visualizes the single photon advantage at the hardware level. Moving on to absence of photon number coherence and its role, which is also related to the 3D part of figure 3. So beyond the brightness and the multi-photon statistics, the security proof requires the emitted light to have vanishing photon number coherence. If there were stable phase relations between the vacuum, single photon and multi-photon components, a dishonest Bob could exploit that extra structure for more powerful attacks. To test this, the experiment sends sequential photons from the quantum dot through a Mach-Zehnder experiment. As we can see in the plot here, the black p-shell trace stays nearly constant as the interferometer phase is varied, with no clear oscillations apart from noise. That means that the emitted light has negligible phase-dependent photon number coherence under the operating conditions used in a protocol. And the control trace, the control experiment shows strong oscillation under resonant excitation. So in comparison, in the graph makes a point very clearly that quasi-resonant p-shell pumping behaves effectively like a phase randomized source while resonant excitation does not. So this year our graph confirms that the quasi-resonant pumping naturally satisfies the security assumptions and we can safely use the phase randomized security bonds without needing an external phase randomizer. Moving on to the Alice part, the dynamic encoding state encoding, the dynamic polarization state encoding at Alice. So in the Alice part, basically Alice encoded each pulse into one of the four polarization states that realize the QSFC single states. Once the source has the right photon number statistics and negligible photon number coherence, the next step is to encode each pulse into one of the four QSCF polarization states for the chosen parameter A equal to 0.9. This is basically done using a fiber-coupled electro-optic modulator driven by a custom FPGA-based arbitrary waveform generator. The FPGA and DACs generate fast voltage patterns, and the EOM converts this voltage into precise rotations on the Poincare sphere. So each 80 megahertz pulse is dynamically prepared in one of the four protocol states. So here I made another code. Basically, I have tried to visualize the geometry of these states compared to the BB4. Here the dashed lines, the gray lines, shows the BB84 states, the horizontal, vertical, diagonal, and anti-diagonal states, while these arrows show the four QSCF states defined by amplitudes A and 1 minus A. As we can see, the QSCF states are slightly tilted compared with the standard BB84 states, and the tilt is chosen so that in the ideal protocol, Alice and Bob have equal maximum cheating probabilities because the angular differences are small. Therefore, we have to be very precise with the voltages. The EOM voltages must be very precisely calibrated. In the second part of my code, I have tried to look at the temporal drive pattern in its looks at the temporal drive pattern and its effect on QBER. So, although the system is clocked at 80 megahertz, the encoding uses a 160 megahertz internal drive with a Manchester style pattern inside each 12.5 nanosecond window. This keeps the average voltage near zero, reduces drift and thermal effects, and stabilizes the polarization states over long random sequences. Experimentally, this gives a QBER of about 2.8%, which is below roughly the 4% threshold needed to retain quantum advantage. In this figure, the black step curve is basically the simulated DAC output driving. We have horizontal lines, which are reference voltages. These are 80 megahertz photon pulses, and this is a 12.5 nanosecond window. Basically, by flipping the voltage halfway through each period, we keep the average voltage near zero. And this is crucial because it reduces DC drift and thermal effects, stabilizing the polarization states over long random sequences. Experimentally, this encoding scheme achieves a QBER of, as I said, about 2.8%, comfortably below the 4% threshold. Moving on to Bob's part. So the incoming polarization encoded photons are analyzed and detected by Bob using a four-state polarization receiver. So instead of an active switch, Bob uses a passive basis choice. A fixed network of optics implements a 50 by 50 random choice between two measurement bases, projecting a photon into a four output channels. Each of these four output channels is monitored by a superconducting nanowire single photon detector SNSPD, and the clicks are recorded by time-taking unit, which is synchronized to Alice 80 MHz clock via trigger at the start of each K-per sequence. So because of this passive 50% basis chance, basis choice, the ideal probability detects state, and we have to basically divide it by 2, this function. So it's simply one half times their geometric overlap squared. In the terms of hardware performance, Bob's receiver has a optical transmission of 0.5, detector efficiency of 85%, and an incredibly low dark count probability of around 10 to the minus 7, 4 into 10 to the minus 7. Moving on to the next part, back-to-back configuration. So before we add the channel loss, the experiment is run first through a back-to-back configuration, a short free space link with 0 dB annotation. This serves as our baseline to isolate internal imper imperfections like detector noise, polarization misalignment. Under these conditions, with our efficient source and high efficiency detectors, it is extremely unlikely that Bob gets zero clicks during a K-pulse sequence, making aborts from photon loss negligible. So From the 0 dB back-to-back case, given the chosen value of k, it is extremely unlikely that Bob receives no clickback at all during the entire k-pulse run. The next shot, this is just a protocol parameters which we are going to be using. The experimental configuration here is chosen, so it's the parameter match those in the protocol simulations. Moving on to the experimental time tests and input-output behavior. So finally, to verify that the apparatus behaves as required, we record time resolved direction statistics across Bob's 4 channel for many realization of k long random sequence. So Alice basically sent a non-sequence of encoded states, and Bob time takes every detection states event so that his detection window can be aligned with Alice's preparation window. In figure 5, the detection events cluster in the unexpected time means as we can see here, showing that the time synchronization is working properly. The figure 5b here shows that the high extension in the correct basis where the correct detector dominates together with the expected projection pattern in the wrong basis. After that, we then compare the ideal theoretical matrix for a equal to 0.9 computed in the next cell using this formula here. So in the 0 dB configuration, the extracted baseline is basically the extracted baseline QBR is about 2.8% as we have said in the past, and the close agreement between the theoretical and experimental datasets show that the source encoder and detection module all operate as assumed in the security analysis. Moving on to the theoretical input-output matrix, which is going to be your ideal baseline. So in this final part, I will compute the ideal theoretical input-output matrix. This is going to serve as our pure baseline under zero loss and zero noise. In this idealized model, the probability that Bob detects psi j, given that Alice prepared psi I, is governed by the Born rule. So, because Bob chooses his passively 50%, the theoretically detection probability is exactly 1 by half, 1 by 2 times their geometric overlay squared. And our code here tries to compute this for all state pairs at protocol parameter a equal to 0.9 and plots it as a heat map. The 0.5 values which on the diagonal we can see here, they show the perfect projection when Bob guesses the correct basis, while the off diagonal 0.32 and 0.180 values arise purely from the designed geometric tilt of the protocol states. In the code cell, we redefine the four QSFP states a equal to 0.9 for a equal to 0.9, and we try to compute the probability of all pairs of prepared and detected states and plot the resulting 4 into 4 matrix as a heat map. So this ideal matrix can be used as a gold standard. At 0 dB, we want the experimental input-output matrix to be as close as possible to this theoretical one. We can also add 3 dB and 6 dB of loss. Any deviations can be understood in terms of these increased errors, dark counts, and missed detections. So finally, to conclude my contribution, I would like to say the experimental hardware driving this QSFP implementation relies on two main components. Firstly, the pure cell enhanced quantum dot source provides a measured G, G, G20 equal to 0.03. This basically drastically suppresses the multi-photon pulses compared to the standard laser, removing Bob's ability to execute photon splitting attacks. Secondly, the high-speed EOM encoder dynamically prepares the protocol states for A equal to 0.9 while maintaining a low QBER 2.8%. By combining this source and fast encoding here, the experiment successfully implements quantum strong coin flipping, which surpasses both classical protocols and weak laser implementation to demonstrate a true single photon quantum advantage beyond QKD. So that's it for my part. Thank you.
Good evening. My name is Varun, and I will cover the final integration and loss analysis portion of the report. So, in this section of the report, we transition from the baseline protocol to a realistic implementation affected by a quantum channel attenuation. Our objective is to rigorously reproduce the findings of this paper, specifically figure 6 and 7, to evaluate how transmission losses impact the security and efficiency of quantum strong coin flipping QSCF. By integrating the theoretical bounds of classical and quantum cheating with experimental imperfections such as dark counts and multi-photon emissions, We demonstrate the inherent fragility of QSCF to bit errors. Ultimately, this section highlights the critical advantage of using deterministic single photon sources SPS over traditional weak coherent pulses, the WCP method, in extending the operational range of distrustful quantum cryptography. So, before starting the calculations, firstly, I would like to focus on the parameters of the setup. So these setups are taken from the research paper itself. The system clock rate R0 is 80 megahertz. The detector transmission for that is for Bob is 0.5. The detector efficiency is 0.85. The total system efficiency is 0.425, which is the product of detector efficiency and detector transmission. Then the baseline QBER E naught is 2.8% and the dark count probability is 4 into 10 to the power minus 7 and the mean photon number mu is 0.0013. And lastly, the state parameter for the quantum gain calculations is 0.9 and the SPS cheating bound is 90%, whereas the WCP cheating bound is 90.3%. So starting from the basics of photon statistics of the weak coherent pulses. So a laser emits a coherent quantum state. So this is the expression for that we can see. Now we define the mean photon number as mu and mu is magnitude of the square of magnitude of alpha. And on further calculating, we can see that probability of probability of detecting n photons is e to the power mu to the power n upon n factorial. So this clearly is a Poisson distribution. Now we come to multi-photon probability. So probability of finding more than two or more than two photons is 1 minus e to the power minus mu e to the power minus mu. Now for small mu, we can use Taylor expansion, and on further solving, we get probability of two or more than two electrons as mu square upon 2. Now real sources deviate from the ideal statistics, so that's why the G square 0 is defined as expectation of nn minus 1 divided by expectation of square of expectation of n. Now for Poisson distribution, we have G square 0 equal to 1, and for single photon source this is very less as compared to 1. So for a real single photon source, this is corrected using this expression. So P multi is equal is approximately equal to G square 0 upon 2 mu square. Then we proceed to detection probability. So let us suppose eta is total transmission channel plus detector. So now each photon survives independently. So for n photons, the P no detection given n photons is 1 minus eta to the power n. Now if we average it over the photon distribution, so we can have it as sigma summation from n equal to 0 to n equal to infinity probability n 1 minus eta to the power n. On further solving, we get this as e to the power minus mu eta. Now for a lossy channel with efficiency eta, the probability of no click is e to the power minus mu eta. Thus the probability of detection will be 1 minus e to the power minus mu eta, and let the dark count probability be PD. So P click total will be as per this formula which we have used. So 1 minus P signal and 1 minus PD. So on further solving and assuming PD to be very small, we get the P click total as 1 minus e to the power minus mu eta plus PD, where PD is the dark count probability. Now we'll proceed to the cheating probability, and firstly we'll calculate it for Alice. So Alice can basically cheat by exploiting multi-photon pulses, and if a pulse has more than two photons, then Alice can either encode multiple bases, and this will later reveal whichever benefits her. So she wins deterministically in these cases. So the total cheating probability of Alice can be calculated as P as probability of single photon multiplied by half plus probability of multiple into 1. So as we discussed earlier, so in case of multiple photons, she will deterministically win. So here we can write it as 1 minus P multi multiplied by half plus P multi. So the cheating probability for Alice can be written as half plus half P multi. Then we'll calculate the cheating probability for Bob. So Bob can only cheat by optimizing the measurement. So Bob basically tries to distinguish the non-orthogonal states. So the maximum success can be given by P optimization, which is half plus half D. In the experiment, noise reduces distinguishably. So we can approximate the D as 1 minus QBER. So the success probability for Bob is half plus half 1 minus QBER. Now for the simulations in this notebook, we use the specific experimental bounds derived in the paper. PSPS cheat is 90% and PWCP cheat is 90.3. So as we discussed earlier in the experimental setup, these values are being used. Now proceeding to the multiple pulse transmission. So if k pulses are sent, the probability of no detection becomes probability of no click for a single pulse to the power k. So for single pulse, it was e to the power minus mu eta as we derived earlier. So the peak no click for all k pulses will become e to the power minus k mu eta. Now the detection probability will be 1 minus e to the power minus k mu eta. So that's basically subtraction of the probability of detection, probability of no detection minus the net probability, which is 1. So now we'll proceed to the honest abort probability. So honest abort probability is basically so before honest abort probability, I would like to discuss the impact of quantum channel. So a realistic quantum channel inevitably introduces attenuation, reducing the probability that a transmitted photon reaches Bob's detector. However, the detector's dark count rate remains constant. The degradation in the SNR, which is basically the signal to noise ratio, causes the quantum bit error ratio to rise. So in this section, we will model how the loss dependent error rate influences the honest abort probability, the likelihood that the protocol terminates purely due to environmental noise or sequence depletion rather than malicious interference. So now we'll proceed to honest abort probability. So abort occurs if there is no detection or detection but incorrect measurement. So dividing into these two cases, case one is the no detection. So as discussed earlier, the probability of no detection is e to the power minus k mu eta, and detection but error. So supposedly our QBER is equals to PE. So we can write this. So the probability for detection is 1 minus P1 and we'll multiply it by PE because that's the QBER. So total abort probability will be P1 plus P2, which can be written as e to the power minus k mu eta plus the P2, which is 1 minus e to the power minus k mu eta, the probability of detection, and multiplied by the QBER. So now we will basically model the error rates and honest aborts. So QBER, which is known as the quantum bit error ratio. So we'll try to model it with the loss. So as the quantum channel introduces attenuation, so as discussed earlier, so this degradation in the SNR causes the error rate E to increase with channel loss, and this is given in the paper. So paper models this loss dependent error as eta system E naught and eta channel plus half P DE upon PDC plus eta system eta channel. So this formula is given in the paper itself. Now honest abort probability PAB. So an honest abort occurs if Bob detects no photons in the k-long sequence or if an error is detected. So because Bob only detects an error when he happens to choose the same measurement basis as Alice, the abort probability due to errors converges to E by 2. So the total honest abort probability is PAB equal to e to the power minus k mu eta total plus 1 minus e to the power minus k mu eta total E by 2. So in this formula, the PE is almost converges to E by 2. So this is this all we have covered. So this function basically calculates the error and PAB, and yeah. So now we'll proceed to the quantum gain, which is the figure 6 of our research paper. So a quantum strong coin flipping protocol is advantageous only if the maximum quantum cheating probability is strictly lower than the classical cheating equivalent. So the classical cheating bound PC is inversely proportional to the honest abort probability. So PC is 1 minus under root PAB by 2. This is given in the paper. Now we define quantum gain as the difference between the classical cheating probability and the quantum cheating bound. So the G is written as PC minus P cheat. Now, if this G is greater than 0, the quantum protocol provides a measurable security advantage. And as channel loss increases, PAB rises, which further lowers the PC. And eventually we can see that this causes a destruction in the quantum gain. So now this is the code for plotting the figure 6. So 6 has two figures, 6A and 6B. So this is basically the code, and here we can see that we have plotted the honest abort probability with respect to the channel loss in decibels, and this we have calculated plotted for different K and E values. and the second figure basically shows the quantum gain, and quantum gain above zero is basically called as quantum advantage. So what all can we infer from figure 6 and 6a and 6b? So from figure 6a we can conclude that as channel loss increases, the oddest about probability rises exponentially, as we can see, and this occurs because higher attenuation prevents signal photons from reaching the detector, leading to a surge in no click protocol aborts, while increasing the pulse sequence length k helps suppress these non-detections. It also accumulates more baseline errors, illustrating the system's extreme sensitivity to channel noise and distance. Now we'll proceed to figure 6b. So in 6b we can clearly see that how quantum advantage breaks down over the distance. And as the honest abort rate climbs with increasing loss, it becomes significantly easier for classical algorithms to hide their cheating within the system's natural noise, which eventually drives the quantum gain below zero. Crucially, this graph also confirms the single photon advantage. The solid curves represent the SPS consistently maintain a higher quantum gain than the dashed WCP curves, allowing the protocol to remain secure under higher attenuation. So here we can clearly see that the SCP curves are above the WCP, which show the quantum advantage of SCP over WCP. Uh, so now we'll proceed to maximum secure coin flipping rate, the figure 7. So to maximize the practical rate of the protocol, we must find the smallest possible sequence length k min that still yields a positive gain, which is g greater than 0 for a given channel loss. So as seen earlier, we can see that PC is 1 minus square root of PAB over 2. So solving this, we get PAB less than 2, 1 minus P cheat square. So solving the PAB formula gives for K gives us K minimum. The maximum secure coin flipping rate R is then limited by the system clock rate. So R is equals to R naught upon K min. So this is the code for figure 7. And now we can see this is our figure 7. So figure 7 is almost a linear figure, but after 10 to the power 2, it basically becomes vertical. So now what all can we infer from figure 7? So from figure 7, we can infer a strict trade-off between the secure coin flipping rate and channel loss. The rate drops exponentially over distance because we must transmit much longer pulse sequence to compensate for the signal loss. The sharp vertical drop to zero represents a hard security cutoff. Once the sequence length exceeds a certain threshold, the cumulative probability of accidental multi-photons emissions becomes so high that malicious photon number splitting attacks become perfectly viable, instantly destroying the quantum advantage. However, the theoretical improved SPS curve suggests that utilizing future state-of-the-art quantum sources with near zero multi-photon emissions would safely extend this security limit up to 30 decibels of loss. So this is it. Thank you.
I will present the experimental result and final analysis of our quantum protocol. This section is extremely important because it answers the three key questions. First, how accurately our system performs. Second, how close we are to the theoretical prediction. And third, whether we achieve a real advantage over a classical system. Now we will begin with the back-to-back configuration, which represents the zero loss regime of the system. In this setup, Alice and Bob are directly connected, which means there is no channel attenuation at all. So what does this imply? It means any error we observe here is not due to channel, but purely due to intrinsic system imperfections. This includes detector noise, polarization misalignment, and imperfect state preparation. This is very important to understand because the configuration gives us a baseline performance. In other words, this tells us the best possible performance limit of our experimental circuit. So later, when we introduce the losses, we can clearly distinguish whether errors are coming from the system or from the channel. So this is not just a setup, but it is a reference point for all the further analysis. Next, we will move to the input-output matrix and analysis. This matrix essentially tells us how accurately the quantum states prepared by Alice are being measured by Bob. The theoretical implementation is given by Eij equals 1 by 2 modulus squared of the overlap between states. The factor 1/2 is very important as it because it is account for random basis selection, which is fundamental in quantum protocol. Phi represents the state prepared by Alice, and the phi j represents the state measured by Bob. In our implementation, we define four quantum states: phi 0, phi 1, phi plus, and phi minus. These represent two different bases, which are essential for quantum encoding. We then compute overlap between all possible points and construct a 4 by 4 cross projection matrix, which was also a probability matrix. Finally, we visualize this matrix using a heat map so, so that we can clearly see the distribution of probabilities. Now comes the most important observation. We observe strong diagonal elements. This means the probability of correct detection is very high. At the same time, the off-diagonal elements are small but not exactly zero. This is extremely meaningful because in an ideal system, this off-diagonal terms would be exactly zero. But in a real experiment, small deviations are unavoidable. This arises due to detector dark counts, imperfect alignment, and limited distinguishability of quantum states. So this matrix is actually telling us two things at once: high accuracy and realistic imperfections. And overall, this confirms that our experimental implementation closely follows the theoretical model. Now we evaluate the quantum bit error rate or QBR. This is one of the most important performance parameters because it is directly quantifies the reliability of the system. It is defined as error counts divided by the total count. In our experiment, we have observed 78 errors out of 1000 total detections. So the QBR comes out to be 2.8%. Now, why is it important? Because for a secure quantum protocol, the error rate must remain below a certain threshold. Our value lies within the theoretical range of 2 to 3%. This close agreement tells us that our system is operating correctly and efficiently. The small difference again comes from detector noises and encoding imperfections. Next, we will analyze the honest about probability. The honest about probability is defined as P about is equal to e raised to minus k mu n plus 1 minus e minus raised to minus k mu n into kVr, where k is the number of pulses, mu is the mean photon number, and n is the detector efficiency. QBR is the quantum bit error rate. For our system, mu is equal to 0.0013, mu is equal to 0.425, QBR is equal to 2.8. Due to the coherent pulse regime, most trials result in no photo detection, leading to a high Hubbard probability, which is nearly equal to 0.999463111. The low Hubbard ensures that the successful detected events are reliable and maintain protocol integrity. Now we come to the most important part of the result, the security comparison. We compare cheating probability across the different systems. So for first classical protocol, we have higher bound. For weak coherent pulse, we have cheating probability nearly equal to 0.903. For single photon source, cheating probability is nearly equal to 0.9. Now, at first glance, this difference may appear very small, but in quantum cryptography, even a small reduction is extremely significant because this pushes the system below the classical security path. This improvement comes from the use of single photon sources, so this directly enhances security and reduces the chances of successful cheating. To conclude, we achieve a low QDR of about 2.8%. The input-output matrix confirms high fidelity. The bird probability remains high, and most important, the cheating probability is below the classical limit. This fact clearly demonstrates the true quantum advantage. Single photon sources are not just an improvement, they are essential for achieving secure and fair quantum protocols beyond classical limitation. Thank you.
These are the project contributions of our group. Murli was responsible to explain the protocol security framework, including honest and cheating probabilities, as well as abort probabilities. He clarified on the concepts related to bias and fairness of their role in quantifying security. He broke down the six steps protocol flow and explained the figure one, provided an intuitive connection between the theoretical definitions and the protocol logic. Namala was responsible for protocol performance simulation. He modeled the weak coin flipping and strong coin flipping cheating probabilities, explained the trade off in protocol rounds, wrote the simulation of cheating probabilities, showcasing the quantum advantage and advantage of SPS over WCP. Krishna was responsible for explaining and covering the experimental setup. He detailed the hardware parameters, wrote the simulation for source characteristics and multi-photon statistics, and built the computational model for the dynamic polarization, encoding, and theoretical input and output matrices. Shaurya I was responsible to cover and reconstruct the central part of the paper through code and plots. I covered the distrustful cryptography needs, coin flipping, explained why laser based sources are very vulnerable, and how single photon sources improve security, reproduced the comparison between WCP and SPS behavior, and explain the plotted advantage region and part of the analysis that links protocol performance to noise, error rate, and channel loss. Varun implemented the theoretical framework of quantum strong coin flipping, derived key probabilities expression, translated them into code, and reproduced the core results by simulating cheating probabilities and rates under realistic condition, including the optimization of protocol parameters and analysis of the loss dependent behavior. Divyansh was responsible to cover the results and analysis section. He computed and analyzed the key performance matrices, including the quantum bit error rate, and interpreted its impact on the system reliability, constructed and compared the experimental input output probability matrices and theoretical prediction to validate system performance, analyzed effect of different photon sources WCP or SPS on cheating probabilities and overall security, organized the result to clearly demonstrate the agreement with the theory and highlight the practical quantum advantage. Thank you.